Hi everyone, Jeffy here, and welcome back to Around the World in Many Days. Today's episode is number 12 and it's titled Under the Surface. Now, we're taking a little break from crosswords this time. This and the next episode will be grid puzzles only. So let's dive in and look at what Gladys has for us this time. So here's the description. Dear puzzling, the first grid is a kakuro puzzle. So let's see, we have two grids here. So we have a kakuro grid here and then another grid with numbers here. So the first grid is a kakuro puzzle. Fill the grid with the numbers 1 to 9 so that each run of consecutive numbers, horizontally or vertically, sums up to the number indicated outside the grid without using any digit more than once. Each digit has a background color, white, gray, or red, and each instance of the same digit in the grid has the same color. In the finished grid, the colors determine what color to use for each of the digits 1 to 9 in the second grid. The second grid forms a Tentai Show puzzle. Along cell borders, divide the grid into rotationally symmetrical rooms. Each room must contain exactly one circle, located in the exact middle of the room. Color every room with the color indicated by the number inside the circle. Today I have squeezed into my wetsuit to explore the underwater world of a lovely small island. Can you guess where I am? Love, Gladys. Okay, so two puzzles and one depends on the other. So we're going to need the numbers from the kakuro to be able to fully solve the Tentai Show. So we're going to look at the kakuro next. The kakuro first and then only after that one look at the other puzzle. So once again, and as always, there's a solvable link here for the Penpa site. So I'm going to open the kakuro first in Penpa and let's see. So let's see what we have. So a normal kakuro puzzle would have numbers in all of these to the left of each row and to on top of each column. Now here we have some question marks, and the reason we can afford question marks in this puzzle is because we also have this coloring, which is not part of normal kakuro rules. So let's say this was the number 1. That would mean that every instance of the number 1 would be a red cell. So you couldn't put a 1 here. You could put a 1 in a red cell only. So that's a bit different. But a lot of the normal kakuro logic still applies. So you can't put the same number in a row or column. You could put a number here and then the same number here, but you can't put it on this stretch. You can't put 2 1s here, for example. And 1 to 9 only. Let's see. So where's the best place to start? So there are some instances here which can only be made one way. For example, the sum of 16. So these are all sums. So sum of 16 from the numbers 1 to 9, it's only going to be 9 plus 7. And there are 2 of these in the next to each other. So one of them is going to be 9 7 like this, and the other is going to be 7 9. Maybe I should change this color because it's pretty hard to see the green from the gray background like this. So this would be a valid way to make these 16s, but obviously this can be the 7 as well. So we're going to use the pencil marking here to indicate that this can be 7 or 9, but it has to be one or the other. And now that we've pencil marked these, we obviously know these are different. So these are 7 and 9 in some order. Those sum to 16. So if this is going to be 22 total, this is going to be 22 minus 16, which is 6. And that we know we can put that as a normal number here. So that's our first digit in the grid. We can also tell something about these numbers here. First of all, they can't be 7, 6, or 9 because those are not white numbers. So we don't know whether 7 is red or black, but we do know it's one or the other. It can't be white. And we can also tell that the sum of these two numbers is going to be 29 minus 16. So these sum to 13. Now, how can you make 13? 13 can be 9 plus 4, but this can't have a 9, so that's impossible. And also there's a 9 already. One of these is already going to be a 9. 13 can be 8 plus 5, which is possible. 8 and 5 are not restricted yet in any way. Or it can be 7 plus 6. Well, 7 is already one of these, so we can't have a second 7 here. So 8, 5 is in fact our only option here. One of these is 8 and one of them is 5. Pencil mark those. Like that. Now, if we look at this stretch here, it has 6 numbers and it only sums up to 21. So that's a pretty low sum for 6 digits. And in fact, it's the lowest it can be. If you sum up 1, 2, 3, 4, 5, 6, that's 21. So in fact, these can only be the numbers 1 to 6. And they all have to be their ones each. In other words, this cannot be 8. 8 would make this sum too large for 21. So this must be 5 then. This is the 8. And now if we look at this sum, this 11, we have an 8 already here. So these are 3. So they're going to be 1 plus 2. And we can pencil mark that as well. 1, 2, and 1, 2. So we already also know that the remaining white digit. I should say though that in the description it said that each color has 3 different digits. So 3, 3, and 3. So we have 2 white digits here. So that there's going to be a third one, but there's not going to be a fourth white digit. So what I'm trying to say is this remaining white digit cannot be 1 or 2, because 1 and 2 are black and red in one order or the other. Now let's see. So what can this number be then? It can't be 1, 2, it can't be 5, 6. So it can be only 3 or 4. That's because remember this column has to be 1 to 6. So 3, 4, you can pencil mark that in as well. Now then, what else can we tell? This 30 sum is not as restricted as this one. There's a lot of leeway when you put 30 here. But if you think about what can go here, obviously it can be 1 or 2. I say obviously, but can it be 1 or 2? It cannot be 1 or 2, sorry. So 1 and 2 are going to be in these two. And you'd think that 1 and 2 can go here, like if this is 1, this can be 2. But then 2 would be red, and this would be a black 2, so it doesn't work. So if I put that in the grid for just a minute. So if this is normal, I'm going to erase this in a bit, but if this is 1 and this is 2, we can't put a 2 here. And we can put a 1 here, obviously, because there's a 1 here. 2 here would be a black 2, and we would have a red 2. That's not allowed. And the other way around, if this is 2, same logic applies. This can't be 1, because 1 would need to be red. So in fact, we do know this is not 1 or 2, and it can't be 5 or 6. So this is also 3 or 4 only. Now that tells us that these are 3 and 4 in some order, so the only thing missing from this column here is 1 and 2. So that must go, those both must go into these bottom cells here. Now then, I want to ask whether this can be 3. And it can't, but it's a bit less straightforward to see why that can't be 3. If we put 3 here, the maximum this can be is 2, so these are 5 then. And we need 25 more for this 30. Well, what's the maximum you can put here? The maximum you could put here is 9, 8, and 7 in some order. And those sum to 24, so you would have 29 only. So if you put 3 here, you can't make the sum work. So this has to be the 4. And precisely the same logic applies to this number here. If you make this one, again, these are 5, and you would need 25 in these 3 cells. Can't do that. So this must be 2. This is the 1. And we know these as well, because now 1 must be red, so that's this one here, and 2 must be black, so this is 2. Still don't know the 7 and 9, but we're going to have to find it in a different place. Obviously, this corner is locked in. There's no more logic to be done in this corner, so we're going to have to find another 7 in the grid and then decide based on that which one is the 7 and which one is the 9. So as we said, now the maximum we can make these are 9 plus 8 plus 7, which is 24. And these are 6, so we need the 24 here. So we can pencil mark something here, 7, 8, 9. And we know better than that actually, because we know 7 and 9 are black and red. So neither can be this number here. So this can only be the 8. So in fact, these are 7, 9. And this cell here is just the 8. Let's look at this 14. So we have an 8, so we need 6, the sum of these to be 6. And the gray cells have 3 options. It's either whatever this is, 7 or 9. But whichever this is, it's going to make this sum way too big. Even if it's 7, 7 plus 8 is already 15, and we would need another number here. So 7 and 8, whatever this is not going to work for these. So it's going to be the 4 and the 2 in some order. So 2 and 4 here. What about this cell here? Can this be 9, considering this sum, 13? 13 minus 9 is 4, and we would have 3 more cells. Well, we can put 1 plus 2 plus 3. That's the minimum we can make this, and that would be 6. So that's too much. So this can't be 9. This has to be the 7. And since we know this is the 7, this must be the 9, and now 9s are reds. So these are the 9s, and these are the 7s. That disambiguates this corner here. And now this 13 still, even with the 7, is very restricted. 7 plus 6, so we would need 6 more. 1 plus 2 plus 3 is already 6. So we would need all of 1, 2, and 3 here. Well, this is 3 and 1 in the row here, so it can only be 2. And in fact, we know the colors of 1, 2, and 3, so we can just put those in. 3 is going to be the white one, and 1 is going to be the red one. Now, there's also some logic that doesn't involve kakuro at all here. For example, this cell, we know what this cell is going to be. Even without this sum, with the question mark, even without looking at this sum, we know what this cell is going to be, because this cell sees 1 and 9, and there's only one other red digit that's going to go there, so that's the 6. And the same is true of this. This now sees 1 and 6 on the row here, so it's going to be the third, the only remaining red digit, which is 9. And with the 9 here, the sum is 14. 9 plus 5 is 14, so this is 5. Then again, this is 3 and 5, the only remaining white digit, 8. And this goes on. This one sees 3 and 8, the only remaining white digit is 5. And I think that's all we can use that logic for. And now we have to look at the sums again for this column, for example. Yeah, so this column now sums to 14, 22, 28. We need 7 more here. Well, if we look at what this, well, this 7 can't go. What these black digits are, the 7 can't go there. We need 7, this to sum to 7. So 7 plus anything is not 7, because this can't be 0, obviously. So this is going to be 2 or 4. Let's pencil mark that for a second there. We can know better than that, obviously. obviously. So to make that 7, this would have to be, with 2 it would be 5, and with 4 it would be 3. So 5 or 3. Did I do that wrong? Let's just see it. 14, 22, 28, and we need 7 more. Oh no, I'm just thinking that 5 and 3 are both white. 2 plus 5 is 7. Oh yeah, it's not, I was thinking we would see which one can be a white digit, but it's actually not that. It's the fact that this C is a 5. This can't be 3. So yeah, confused myself there, but yeah, this can't be 5 because of this 5. And in fact, we could have known this already by the fact that it sees 5 and 8. So this is a 3. Now this, to make this sum 7 and this sum to 35, it has to be 4. This has to be 2, and this has to be 4. And now we can look at this sum as well. So this is 6 digits, sum to 21. Does that sound familiar? Maybe it does, because this column is exactly the same. It's just the numbers 1 to 6. And what we're missing is 4 and 6. So 6 is red here, and 4 is gray. And now this corner fills itself pretty easily, because this digit here sees 6 and 1. It can only be 9 out of the red ones. And now this sees 9 and 1, it can only be 6. This is 9 and 6, it can only be 1. And this is 6 and 1, it can only be 9. And that's the solution to the kakuro. And from that, we now know what color each of these numbers is going to be in the next puzzle, in the Tentai Show. So we are going to swap to that one next. Solve the Tentai Show grid first, and once we have a finished grid, then we're going to come back to this and look at the colors. So I'm going to open my Tentai Show, zoom out a little bit. Okay, here we are. So how does Tentai Show work? So you make these, divide this grid into rooms. So let's say every room has to have one of these circles in the center of it. So for example, this would be a valid room. So because the 5 is in the center of it. And the other thing a room must do is it must be rotationally symmetrical. Now what does that mean? It means that we can't make a room like this, because everything that's on this side must be on the other side from the center point as well. So if we have this inside the room, this must be inside the room as well. Now this is rotationally symmetrical. And you can think of it as, if you turn it upside down, it's the same form. It makes the same kind of room. You can turn it upside down and it remains the same. So this would be a valid room. It's symmetrical by this middle point here. And every room must have one of these circles and only one of them. So what does that tell us? Well, the easiest way to start, the really simple thing, is that if you have two numbers in cells that are next to each other, you must separate those, because they can't be part of the same room. So everything that's next to another number, you can just separate those. And there are a lot of these in the grid, but I think we can do better than that, and we can also, when we fill in a line here, we can also fill in its counterpart line on the other side of the room. So we know this is part of this room because this cell is going to be part of it. So if this wall is in the room, then this must also be a wall, because it has to be symmetrical. If this wall wasn't here, it wouldn't be symmetrical. So symmetrical, when looking from this 7, we can make this wall. And the same is true of this wall and this. It has to be symmetrical, so these have to be at the same distance from the center point. And same here with this 8, this room. To keep the symmetry, we must fill these walls as well. And this wall symmetrically is going to be here. This wall symmetrically is going to be here. This wall going to be here, and this wall going to be here. And not only the walls that we fill here, also if you think about the rim of the grid, this is a border of the room, so there has to be a symmetrical border here and symmetrical border here. And now for this 4, this is a border, so symmetrically this must be a border, and this is a border, this must be a border. So we already get some of these little rooms just by filling in these basic rules. So again, wall here, symmetrically wall here. Wall here and here, so symmetrically these are all walls. This wall must be here symmetrically, and this wall symmetrically here. What else is next to another number? These are next to each other because this cell is part of this room and this cell is part of this room. So that has to be a wall symmetrically on both sides. This wall symmetrically is here. And this wall also symmetrically to the 2 is here. And that gives us a wall here and here. These are next to the rim of the grid, so these are going to be the symmetrical walls here, and then divide these symmetrically here. Symmetrically to the 8 we get this. These are next to each other, this 1 and 9, separate those. Symmetrical wall here, symmetrical wall on this side. This is next to the rim, so here. This is 9 is next to the rim, so this is a wall. And symmetrically this must be a wall as well. Then separate this 6 and 2, symmetrically here and here. Separate this 9 and 2 and the symmetrical ones on both sides. This 6 is next to the border of the grid, so that must be a wall. This 6 must have a symmetrical wall here. And there's a lot of this sort of preliminary logic that doesn't really require any sort of great deductions. I'll just fill in because it's all the same things we've gone through several times. Now these are both going to be walls, so this corner also going to have walls in the same spots. This is next to the rim. Anything else? These must be divided symmetrically on both sides. Anything else I missed? Okay, this 8 has this corner, so it has to have the symmetrical corner here. This one next to the border, so it can be filled in here. 7 must have this symmetrically here. And is that all for the basic stuff? No, there's a wall here, symmetrically must be here. Okay. And we must divide this 6 and 9, by the way. These are maybe harder to see because they're further apart, but this cell is part of the 6 and this cell is part of the 9, so this must be separated. Okay, now then, continuing from here, we see some cells immediately that can only be part of one room. So this cell is going to be part of this 6. So all of these walls are going to have counterparts on the other side. So here, here, and here. That fills in this 6 room already. Also this wall fills in the 9 room, and this wall fills in the 6 room. Also here, both of these cells are going to be part of the 6 room. Nothing else can reach that. So all of these walls are going to have symmetrical counterparts here. And yeah, there was one more wall we missed because this is next to the border of the grid. Now then, let's see what can go here. And we can look at the candidate sort of rooms. So also we're missing a wall here. This 2 can reach here because the symmetrical counterpart would be here, and this is free. So these are all possible. This is possible. Can it be this 2? Well, it can't be, because it would have to go here and then to the right, which means symmetrically it would go here and clash with this 6. This cell can't be part of this 2. Can't be part of this 2 because it would go off the grid. It would be here, and the same story is true of everything that's above this line. Can't be part of this 2 because it would need 3 cells here and this 6 is in the way. Could it be part of this 6? Well, it can't, because, okay, we have a wall missing here because we have to separate this 6 and 4. It can't be the part of the 6. Can't be part of this 2 because it would be, how many cells? 5 cells. It would be like here, where this 5 is. And it can't be any further away because it would be off the grid here. So we can say, we should probably look at whether it can be part of this 9. So that's 4 cells this way and then 2 this way. So 4 cells here and 2 cells this way. So it would be here, and that would clash with the 8. So it can't be part of this 9 either. Long story short, it can only be part of this 2. So it goes here, so symmetrically must go here and have these 2 walls, these 3 walls here. And symmetrically, since we have a wall here, this must be a wall as well. Now then, can we say something about this corner cell? Obviously it can be part of this one because this is empty. It could be like this. This is valid. Now, can something else reach this cell? And I think it's very easy to see that it doesn't. For a 6 it would be here, clashes with a lot of things. For a 9 it would be 2, 2, and 1, 2, 2, and 1. It would be here. That's a taken cell. For the 2 it would be 3 diagonally. So 1, 2, 3 would be here. That's not even a free cell, and there's no way for the 2 to reach that anyway. And for the 4 it would be 4 to the right and 2 up, so 4 to the left and 2 down. So I mean, there's no way for the 4 to get there. So all in all, the 1 is going to contain this and this. So all these walls are going to have counterparts on this side. Now that also gives us a cell that can only be part of this 6. So 3 walls symmetrically here. That also solves this 2. This must now be a 1 cell room. And it gives us this cell here. This cell it has only 3 numbers that it can reach. Well, it can't reach this because it would be there. First of all, you can't have a wall inside the room, and second of all, this can't reach there anyway. These 2 can't reach there because it would need to reach there symmetrically, and that would clash with the 7, go through this wall. So the only option for this cell is this 9. So that means symmetrically this and this are going to be part of the 9. So these walls have to be symmetrically here and here. And these walls are going to be symmetrically here and here. Now we don't know whether this is a wall because this 9 could continue here and here. So we can't draw a wall here. This cell now, since we drew a wall here, this cell can only be part of the 6, and symmetrically it goes there. Solves the 2. And now we see this cell. So this was part of the 9. This was happening. This now can't be part of the 2, and that's the only other option, only other number it sees. If it's part of the 2, it clashes with the 6. This is the symmetrical cell. So it can only be part of the 9. So this is part of the 9 now. This is part of the 9 symmetrically. And now these 2 walls have to have counterparts here and here. And once we draw that, we see that this can only be part of the 9 as well. So 2 diagonally from the 9, this cell has to be part of the 9. So we separate it from the 2, complete the 2, and now we have a cell that can only be part of the 6. So it goes here. Fill these 3 walls on that side. that completes the 4. This wall completes there. And we have a lot of sort of finished rooms already on this side of the board. Now this 6 had these symmetrical cells. It also contains this, which can only be part of this 6, so it must have these symmetrical walls here, which completes our 9, which completes our 4 here. And now this 9 has 2 cells here, which can only be part of this 9. So these symmetrical cells must be part of it, and that must be a wall. And there must be a symmetrical wall here. This cell must be part of the 8, so the symmetrical cell is here. Separate that one from the 4, that solves the 4. This cell, only 2 options, the 5 and the 2, and if we use the 2, then it goes here and clashes with the 5. It has to be part of the 5, which means these 2 walls symmetrically have to be here and here. That's also 2 here. Gives us a cell that can only be part of the 1, so these 3 walls must be replicated here. Gives us a 1 cell 5 here. Now this cell must be the part of the 2, so symmetrically here. That completes the 2. Then this one room here contains this cell, so it must contain this cell. Draw the walls, and now this must be replicated on this side. This cell is part of the 5, so this cell must also be part of the 5. It has 3 walls here, so 3 walls here. This wall symmetrically is here, which symmetrically is here and completes the 8. This is part of the 2 now, so that completes our 2 here, completes a 5 here, and completes a 2 here. And now, similarly to this 9, we also see these 2 cells only have this option of being part of this 9. So these 2 are the symmetrical parts, and that's our 9 rectangle here. Now, this looks like our 5 is going to be a 9 cell square, but does it have to be? This cell cannot be part of the 7, it would be here. There's no way to reach it. Can't be part of the 2, it would be off the grid. Can't be part of this 2, it would be off the grid. So this corner cell here with the 2 walls must be part of the 5. So this is also part of the 5. This cell also can't be reached by anything. For the 7 it would be there, and anything else would be off the grid. So this wall also here looks like this can't be reached by anything. So this is in fact a square of 5 cells forming the 9. Now this cell, only option is 7, so counterpart is here. The 8 is finished by this wall symmetrically here. Now, do we know something about this 5 here? I think we do, because this cell cannot be part of this 2. It would be here symmetrically, breaking this wall. So it must be part of the 5, so that means this must be part of the 5. So we have a wall here, so we have an entire wall here, so we must have an entire wall here. That's also 2. Gives us a cell that must be part of the 7, an additional cell for the 7. So it must go there, and that's completed the 2. And we were correct, we were shown that was the solution to the Tentai Show. Now then, if you look at this grid, you see absolutely nothing, or I don't know if you can see it, but I don't see anything without doing the coloring. So we are going to need the coloring from the previous grid to give us the answer. So let's see. I'm trying to put them both on the same page if I can somehow. Does that work? Yeah, we can see all the numbers here. So we don't have to do anything about the whites. This is already a white background. But we do need to do something about the reds. So reds are going to be 1, 6, and 9. So every 1, 6, and 9, we need to color red in this grid. So 1s and 6s. 6s here, and 9s. So this is a 9, this is a 9, this is a 9, this is a 9, 9. Is that all? I think it's all. So that's all the reds, and now all the grays. The grays are 2, 4, and 7. So 2s, are going to be gray. Is that all 2s? 4s, and 7s. That looks like that's all our coloring done. Now what did we make? We have some sort of red and white background. Did I say background? Background, red and white background. And we have some writing on top of it. So this is the flag of Malta, the Republic of Malta. It has this cross here. It's not exactly like a red cross like that, but it's an approximation of that, and then half red, half white. And the writing says that's a G here, there's an O, Z, and O. So that says Gozo. So that's going to be our final answer. The final answer, if you remember, we were looking for the name of an island where you can do diving. So we are in fact in Gozo. So let's look up that next. Gozo is one of the islands of Malta in the Mediterranean Sea. So that's where Gladys is this time. That was our final answer. Let's look at our map where we are this time. So last time we were in Jerba, so Morocco, Algeria, Tunisia. Now we are in Gozo, so we are crossing the Mediterranean here, about halfway through, and yeah, this is the first time we have actually left Africa. So the journey continues. We are in Gozo, and that is it for episode 12. Now episode 13 is going to be titled Coasting Along the Coast. And yeah, as I said earlier, it's not a crossword. It has two grid puzzles as well. So there's a star battle puzzle, and then there's a Philomeno to solve. So that's what we're going to look at next, and thanks for watching.